In this video, I'm going to introduce a method for solving maze. Let me describe this problem briefly. Here we have 70 by 70 maze, and we start from left top and end at right bottom. In this problem, our goal is maximize the score. Our initial score is 500 points, and it costs 1 point for 2 movements, and 15 points for yellow point cell, and 500 points for large point cell. There will be 50 yellow point cell at randomly, and large point cell will appear only at left bottom or right top. The maze is given by the 70 by 70 square matrix, and the matrix consists of numbers. 0 means empty cell, 1 means wall cell, 2 means small point cell, and 4 means large point cell. So input will be given by the concatenation of rows of this matrix, and output should be like this. Now let's define state graph and search tree. The state graph, this is the one possible way to make state graph. Those are the cells like 0.0 or 0.1. And we connect the two nodes if we can go one node to the another. And we can transform this state graph to search tree. However, the problem is there are too many nodes. There are 2,500 nodes in state graph and 3 to the 140 nodes in search tree. So how can we define state graph in a much smarter way? As you can see, suppose you are at the start point and there are only one way to go, and then you will meet junction. If you go this way, you are blocked, and if you could go this way, you will meet another junction. So we mark every junction and block cell, and we connect them to make a state graph like this. As you can see, there are only 17 nodes in the state graph, so as the search tree. So we reduce the problem. Now I'm gonna introduce the method of pruning block tree. A block tree is a subtree that has no goal node. In this example, this is an example of the root of block tree, and this is another example, and this is another example. So we don't have to visit the block tree, right? Actually, no, because we can get points from visiting the block tree. Now imagine you are at node X. If you visit node Y and come back, you will lose 9 points, like this. 45 minus 54 is minus 9, and I write this at the left. Now, what if we just go and take points and come back? I want to ask, how many point cell would you take? If you take 1 point cell, you will get 7 points. And if you take 2 point cell, you will get 16 points. And if you take all of the point cell, you will lose 1 point. So you may want to get 16 points. So I write this at the left. Now let's apply this to the example of the right side. Imagine you are at node F and you would just take the points because you can get 7 points. Now, if you are at node D, you can get 17 points for just taking the point, and you will lose 2 points for visiting the node F. However, at node F you can get 7 points, so you can get 5 points by visiting the node F. However, the winner is 17, so you're just taking the points. And for node G, you would just taking the points because you can get 2 points from taking the points. So finally you will get 19 points from node D. Similarly, at node D, you can get 10 points by taking the points, and you will lose 5 points by visiting the node D. However, you can get 19 points by visiting the node D, so you can get 14 points by visiting the node D. The winner is 14, so you would visit node D. Do you want to visit node E? No, obviously. So for the node A, you can get 4 points by taking the point, and you can get 2 points by visiting node B. So you would visit node B, and then you can get 16 points. And from node A to node C, you would just taking the points because you can get 10 points. Total, you can get 26 points from node A by visiting the every subtrees. After the pruning process, you would write 26 at this node. This means you can get 26 points by visiting the every subtree. So here you don't care about the subtrees. You only have to care this side. So the state graph becomes much more smaller. Now I'm gonna prove the optimality of this method. The definition of tree is connected acyclic graph. This means a cyclic state graph is tree. The property of tree is there is only one way to go from the root node to any node in the tree. And the other nodes are just block tree. So after the pruning process, like this, only one way path is left with maximum score. Since there is only one path and we computed the maximum score that you can get from visiting the all subtrees, you will get 25 points from this node, you will get 500 points from this node, you will get 10 points from this node, and you will get 7 points from this node, and you will go to the goal node. Since we computed maximum score for each node you can get from visiting the every subtrees, the maximum score from this maze is 25 plus 500 plus 10 plus 7, and the initial score 500 equals 1042. This means you can get the maximum 1042 points from this maze. Now, what if there is a cycle in the maze? In this maze, you can also make state graph and you can prune block trees. Since we are dealing with only 70 by 70 maze, the small state graph may left after the pruning process. Then you can search every path to find optimal path. At last, I want to discuss pros and cons of this method. We have to visit every node for pruning, and after the pruning process, this problem is same as graph search problem. So the cons is, for a very big and complicated cyclic maze, we cannot compute the optimal path in polynomial time. However, practically, like in our problem, we're only dealing with 70 by 70 maze. This method can find the optimal path quickly. Okay, I hope you enjoyed this video. And if you want to try solving this maze, download the sample maze by the link below. Thank you.